Hey guys, this is chapter 5, the X-ray tube. So we're going to go over some of these parts. Hopefully if anything was confusing, it'll help make a little bit more sense. And you can see I've already drawn some of it out. So hopefully you can read that. And what we'll do is we're talking about the X-ray tube, and the tube is actually this part right here. This is the evacuated glass or metal envelope that we typically call the tube. And that is sitting inside this protective housing around it. And then we've got the collimator attached, so that when we're actually moving the tube in the department, we're actually moving all of this. We're moving the actual X-ray tube, the protective housing, and the collimator because they're all attached to each other. Okay, so when we talk about this, let's start with the protective housing because that's how the chapter starts. So this protective housing, which is all of this out here, is actually made of different metals. Okay, and part of the purpose of that is to help dissipate some of the heat that's created in here. Remember, when we make an X-ray exposure, 99% of its heat, 1% is actual X-ray production. So this housing helps to protect the patient, the technologist, from the heat that's generated. If you remember in the beginning chapters, they showed just this right over the patient with the electrical cables attached to it. So we don't do that anymore because they talk about how electrocution was very real in the early days, and that's not a thing that we typically deal with now. So this protective housing does allow for 2 electrical cables to come in. They come in and go to each of the electrodes. So we have the anode line comes in, and remember that's the positive electrode. And we have the cathode line, which is the negative electrode. And remember, when you have 2 electrodes, that equals a diode. And a diode only allows electron flow in one direction. Okay? It typically will flow from negative to positive. So the X-rays, when they're created from electrons that will travel from the negative side of the tube over to the positive side. That's the only way they'll travel. If they ever were to travel the other way, this tube would actually implode, right? So they travel from negative to positive. If they ever went in any other direction, the tube itself would implode, all right? So we have 2 electrodes, anode positive, cathode is negative. That creates a diode. Now, we also have on the anode side, we have an induction motor, and the induction motor is made up of the rotor and the stators. Both of those components make up the induction motor. So these stators are supplied with electricity, and that actually turns the rotor. And when the rotor turns, it turns this anode target, all right? So the induction motor is made up of the stator and the rotors. Remember, the stators are outside the glass envelope, and the rotor is actually inside the glass or metal envelope. The anode target, it spins. Remember, that spins, it says on a general purpose tube, up to 3,400 revolutions per minute. On a specialty tube, it rolls at 10,000 RPM. Okay, so this revolves or spins 3,400 RPM. On the anode, the face of the target is made of these 3 elements. Or I'm sorry, the face is actually made of tungsten, which is 74, and rhenium, which is number 75. The molybdenum comes into play because the back part and the core of it is actually made of molybdenum. And then it attaches here where there's some copper. And the molybdenum and the copper help to pull the heat that's created back off the anode, all right? On the cathode side, we actually have the filaments and the focusing cup. So you have 2 filaments on a general purpose tube. You typically have a large filament and a small filament, and literally one is longer and the other one is shorter. So a large filament and a small filament. And those filaments are made of tungsten and thorium. It's about 1 to 2% thorium, and the bulk of it is tungsten. And the reason they make this an alloy and this an alloy is because it tends to make it stronger. It has more tensile strength, and that's actually when you're creating an alloy, when you mix 2 metals together. These filaments sit inside a focusing cup, and the purpose of this focusing cup is to guide the electrons. Once we talk about releasing them, it guides these electrons across the tube, so it focuses them in the direction you want them to go. So it has a negative charge on there, which actually works to keep the electrons together in the beginning, and then eventually it sends those electrons across. And the focusing cup is made of number 28, which is nickel. All right. This whole thing, if this is a glass or a metal enclosure, if it's made of glass, it's typically made of what's called borosilicate glass or Pyrex, which we use that a lot in baking. The reason they make things out of Pyrex is because it can withstand high amounts of heat. So this has to be able to withstand the large amount of heat that's created when we produce x-rays. It could also be made of metal, which if it's a metal enclosure, it tends to give us more tube life because it can withstand the heat better. And they talk about the fact that tungsten can vaporize down here on the bottom, and it's called the suntan effect or a gassy tube. And if it vaporizes down here, then sometimes what can happen is the electrons can actually arc to the tungsten, and that can create a spark, and this whole thing would implode and break. So when they're made of metal, much better tube life. But when they're made of glass, that they work. It's just typically made of what's called borosilicate glass. This entire envelope that's evacuated, fully evacuated, there's no air in it whatsoever. That evacuated envelope sits inside this protective housing, and between the housing and the glass, or the housing and the metal, we have this dielectric oil that just fills this whole space. Doesn't get around the stators, but it fills the space in between, which also helps dissipate some of the heat that's actually created. In the metal or glass enclosure, this area, now I made it look thicker, which is weird because what I'm going to tell you is that the window is actually a thinner portion of glass or a thinner portion of metal, so that when the x-rays are created, they actually exit out of the window. When they exit out of the window, it's just much better. It's easier for them to pass through the thinner portion of glass. And realistically, this anode should be directly over it, or the window would have to be over here. My drawing's a little off. You'll have to forgive me, but when they're created, ideally you want them to come down right here. So our window should be right here, or I should have pulled the anode out more to have it fall over here. All right, so the dielectric oil bathes that tube and kind of cools it down. All right, attached to this, we have a collimator. And the purpose of the collimator, there's two knobs on the front that we actually turn that helps control the light field. And it makes your light field, which is in theory everywhere the light touches, radiation touches. So you collimate so that you're only radiating the area that you intend to. Okay, and that's the collimator, which is attached to that. Now, hopefully that clears up what is actually in the tube. Again, anode side, positive, cathode side is negative. This is a fully evacuated glass envelope. A little bit different when Rankine originally used the Crookes tube. It was partially evacuated, meaning it still had some air in there, which the electrons interfered with when he was creating x-rays. This fully evacuated is a modern tube called a Coolidge tube, and this is exactly what we still use today. Coolidge came up with this, I believe, in 1913. So literally from 1913 to 2020, we are still using fully evacuated glass tubes that are exactly like that. The original glass tubes were hand blown. Now they're manufactured, but the original ones, glass blowers used to blow the tubes, and then they would evacuate the air out of them, which gave it like a little dimple. Okay. The collimator, the purpose of the collimator is to adjust your field size or your radiation exposure size. And again, 2 electrodes make it a diode, which means that electrons will only flow in one direction, from negative to positive. All right, I'm going to flip the page here, and we're going to look at actually how the x-rays are produced. Okay, so when we flip that, notice all I gave us on this page was an anode target, the stators, which would be outside the envelope, and the rotor, which turns it, because that's what we have in most general purpose tubes. And then I gave us a focusing cup, which is negatively charged, made of nickel. I gave us just one filament so that we can look at that. I gave us a focal spot, which is the exact area where electrons are converted into photons of energy. Okay, and we're going to list a couple things before we get started just to say what controls what. All right, so on the control panel, we tend to set our KVP, we set our MA, and our time. All right, and our time is always in seconds. And together these two things make what is called milliampere seconds. Milliamperage, milliamperage is 1/1000th of an ampere, and kilovolts, kilo means 1,000, so kilovolts would be thousands of. So if we say we're set at 50 kVp, it's 50,000 volts, or 50 kVp, kilovolts. The P just means the peak. And then we also choose our focal spot. And remember, focal spot has to do with the resolution of the image. How clear is it going to be? How crisp is it going to be? So you're either choosing small or large, and that determines which filament is going to heat, and it determines the resolution on your image. So it determines the resolution. Now, when you choose that, your mass value, your MA and your time, what that controls is the quantity of the beam. And when I say it controls the quantity, it controls the number of electrons released from the filament. Okay, the number of electrons released from the filament. And ultimately, it controls the number of photons that are created. Right, so it controls the number of electrons released from the filament and the number of photons that are created ultimately. Our KVP actually controls the penetrability of the beam. How penetrating is it going to be? Controls the penetrability of the beam. And it also has a part, it plays a part in the number of photons. And we'll talk about that in a minute. So this represents the quantity, and KVP controls the quantity, and it also controls the penetrability, which is the quality of the beam. Okay, so KVP controls your quality and your quantity. How penetrating is it going to be? So the KVP determines if you get a photon that looks like this, or if you get a photon that looks like this. So this would be more penetrating than this one would be. All right, now that we said that, let's go and take it to the tube level and talk about that. So this is the cathode side of the tube, correct? This is the cathode, so it's negative. This is the anode, and this side is positive. And remember, this means that it's a diode. So when it's a diode, the electrons are going to only flow from negative. They're going to flow from negative to positive. If they flow the other way, the tube would implode. So they talk about in there that depending on your mass setting, that what happens over here when we first start to depress the switch, two things happen. This starts to spin the anode up to speed, correct? So when we first depress the switch, this starts to spin, and remember, this spins at about 3,400 RPM. Okay, it spins at 3,400 RPM, or revolutions per minute. That's a general purpose tube. That starts to spin, and on this side, the filament heats, whichever one you chose. The filament heats to incandescence. And remember, incandescence is 2200 degrees Celsius or 3192 degrees Fahrenheit. Right? So, incandescence, this gets white hot. Remember, this incandescence means white hot. And that's happening, this is happening at the same time that this is spinning. And what it does when it gets white hot, it actually releases electrons. This is called thermionic emission. And thermionic emission is when this filament gets hot and it releases electrons. And these electrons form a space charge or an electron cloud. Okay, so all these electrons get released. Now, how many get released? A ridiculous number. I will tell you that if you were set at one mass, okay, we'll make a little side note down here. If you were set at one mass, you would release 6.24 times 10 to the 15th electrons, which is 6.24 million billion, or 624 with 13 zeros behind it. Okay? These are all equal numbers. This is this is this. Now, out of that, that's the potential number of photons that we can create. So when we create X-rays, it's about 1% of that. So I said to you in lecture, if I won that in lotto, and I said I just won $6.24 billion, and I'm going to give you 1% of that, you wouldn't tell me no, because 1% of that number is a ridiculously large number. So that's the potential of the number of photons that are created. Now, can we see electrons? No. Can we see photons? Absolutely not. We can't see any of this, so we can't visualize it. It's theory, but we know that it works based on people that are way smarter than me, that have come way before me, that have said this is what happens. Okay? So thermionic emission is the process of building this space charge or this electron cloud. That's what this is. And I'm not going to take the time to write everything. You'll have to pause me and write this so that it makes sense. But we build this space charge or electron cloud by heating this filament to incandescence. That is called thermionic emission, the process of releasing electrons from a heated filament. The product that you get from that is this space charge or electron cloud, okay? And that is this right here. This is your space charge or electron cloud. Both names are the same. I'm just going to do that. You can reference them either way because it seems like in our field everything has two names. So you build this at the same time you're getting this to spin to speed. Right? And this all happens when you push the first portion of the switch. So this is the rotor portion. And the rotor portion, this starts to spin up to 3,400 RPM. This releases the number of electrons you need. Now, this number of electrons is based on your mass setting. So whatever your setting is, that's how many electrons are going to be released from this heated filament. Okay? Now, so that takes care of your mass. Where does kVp come in? kVp determines how penetrating that beam is, right? So kVp is the potential difference between the negative and the positive. So your potential difference is your kVp setting. It's your kVp setting. And it's the difference between the negative and the positive. Meaning how how strong is the degree of attraction between them. So when you end up having the exposure getting to take place, the cathode becomes more negative, the anode becomes more positive. So imagine if you had two magnets and you had opposite ends towards each other and you could heighten their magnetic strength. It would make them more attracted to each other, right? So what you're trying to do is pull the electrons away from the cathode and have them pull and smash over into the anode. Because at this point right here, they have potential energy. They're not going anywhere. When they start to move, they move across with kinetic energy, right? And remember, they move from here to here, which in reality is about this big of a distance. They move from here to here at least half the speed of light. Okay, so they move from negative to positive. So when they start to move across, they move with kinetic energy. So they come across, all these electrons come across, they're heading towards the anode. All of them at the same time are bombarding that target. All right, so they move from the cathode over to the anode. And remember, they come across in a stream, but because of the angle of the target, remember, they come out thinner. That's called the line focus principle. So when these electrons smash into that focal spot, all of that kinetic energy from the electron is released as a photon. All of them. And they all come at different wavelengths. They're not all the same. The highest wavelength, the highest amount of penetrability that you would get would be whatever your KVP was set at. But notice that the wavelengths are different on here, right? Meaning that some of them are weaker, like this wavelength is longer than this one, but this one's longer than this one. So that's where you get that it determines the penetrability of the beam. And the beam, this that's coming out, that is your primary beam. Okay, this right here is your primary beam that is released from the X-ray tube heading down towards the patient. Not primary tube, I'm so sorry, primary beam. That is the primary beam, not the tube. Okay, primary beam, not the tube. Okay, primary beam is right here. Here, I'll write it here. Primary beam is the beam that heads out of the tube directed towards the patient. So this beam is polyenergetic, meaning it's made up of multiple energies. It's not all the same. Whatever I'm set at, it's not all coming out at the same strength, because if it came out at the same strength or the same penetrability, it would blow through the part the same way. So it comes out at different, so that some of those photons will pass through and strike the image receptor, some will be absorbed in the body part, and some will actually strike the body part and scatter, change direction, lose energy. So when these photons pass through the patient, they either pass through unaffected, they get absorbed, or they scatter. Those are the only three things that that photon can do. Okay, so you start out with electrons. They come across at least half the speed of light, and they all end up smashing into, ideally they smash into that focal spot. And when they smash into that focal spot, they're moving across with kinetic energy, and then this is where they become photons. Okay, so this starts out as an electron, and it converts this into electromagnetic energy in the form of a photon. And what we end up with when this happens, 99% of what we create is heat on this target, and only 1% is actual X-ray photons. So we create 99%, we end up with heat, 1% is actual X-ray, okay, photons, X-ray photons. But when I say that and we put a number to it, what I'm saying is 1% of that, and if you were set at more than one mass, that number would be higher. So 1% of this is the number of photons in the beam. 99% of this is the heat that is created. And that's why we have things in the tube that help dissipate the heat, like the dielectric oil, the lead or the metals, the lead and other metals that are in the housing help pull it. If there's a cooling fan, that helps cool it. The fact that this spins helps cool it, because 99% of this number, or whatever your mass value is, turns into heat. 1% actually turns into X-ray photons. Remember that these come across at least half the speed of light. And what I wanted to tell you is how our KVP affects it is, if our KVP is higher, let's say our KVP is set at 100, these are going to come across faster so that they smash into that harder, and they end up giving you this. So if we were set at 100, it's going to give you this really tight, short wavelength, an increase in frequency, an increase in energy. But if we were set at 50 kVp, just random numbers that I'm using, if we were set at 50 kVp, we would end up with a longer wavelength, lower frequency, lower energy. So this is more likely to blow through a part. This is more likely to be absorbed or not pass through as easily, depending on what it is. If you're talking about bone, this potentially could go through the bone. This would ideally be absorbed in the bone. Okay? So the KVP setting determines how negative this is and how positive this is. It determines how strong the degree of attraction is to pull those electrons across. I also said to you that it controls quantity. Now, why does it control quantity? Does it make sense that if I was set at 50, it's going to pull a certain number of electrons across? Again, you're talking about millions of billions of electrons, but it's going to actually pull. I feel like you can't see that side anymore. So sorry. It's going to pull that a certain number of electrons, but the higher your KVP, remember, the stronger the degree of attraction. So when the KVP is higher, it pulls more of them so that more of them go across to potentially make more photons. So when you have higher KVP, you have a more penetrating beam and you have more photons in the beam. So it controls two things, but your mass value only helps control the number of electrons that are released from the heated filament, which ultimately helps control the number of photons that you create. All right. One more thing I wanted to tell you is the melting point of tungsten, which I don't think I mentioned that, but we said that in order for it to get white hot, it has to reach at least 2200 degrees Celsius or 3192 degrees Fahrenheit. The melting point of tungsten is 3400 degrees Celsius, which is 6152 degrees Fahrenheit. So extremely high melting points on materials that are in this X-ray tubes, all for the reason that 99% of what we create is heat. The only other thing I'll tell you is that this interaction that takes place right here, that literally is all of chapter 6 that we discuss. Okay? All right, well, hopefully you can see that. I will zoom in for you so that if you are missing anything, you can hopefully get that before everything shuts down. All right, so this is actually how the X-rays are created when they come across, and this is just one more look at the tube and all the components in that tube. All right, the line focus principle, just to kind of reiterate that and show you on this one, the line focus principle basically says that you can send these electrons across in a thick stream over to the anode target. You can send them across that way, and because of this angle, when they actually come out, what you get is a much smaller, this is your effective focal spot. That's your effective focal spot, and this purple line here is your actual focal spot. Meaning that when you send these electrons across, they're interacting with this entire area right here, okay? All of this. But because of that angle, they're coming out much narrower, which, remember, focal spot always has to do with your resolution. So that's what we were talking about. We were talking about how you send them across, but because of that angle, which on most general purpose tubes, remember that this is a 12-degree target angle, typically a 12-degree angle. They range from 7 to 18, but most are 12-degree target angles. So that is your line focus principle that we just discussed. All right, and then the only other thing that might have been a little screwy when we actually talk about creating the x-rays, remember we have the anode heel effect, which says that some of the radiation is going to be absorbed in the heel of the anode, whereas on this side, there's nothing to interfere. So you tend to have more quantity on the cathode side versus the anode side because some of the photons get absorbed. And that, I usually call it fat cat, meaning you want to put the thicker portion of the patient under the cathode side and the thinner portion under the anode side so that you get more even penetration. All right, that concludes our visual on chapter 5. Hopefully that cleared anything up. If it didn't, be sure to get with me and I'll help make that make a little bit more sense. All right, you guys, have a good day.